In this lesson, we're going to continue talking about model building. Specifically in this lesson, we're going to talk about the best subsets or all possible models in terms of R squared adjusted, the root, mean squared error, and then a statistic called MaloCP, all using the cement example. So recall last class we talked about these step selection procedures, forward, backward, and stepwise. Uh, these methods, again, are more of the historical approach, mostly because we didn't have the computational power. What we're going to be looking at now is the best subsets or all possible models given our predictors, and how we're going to compare these models and potentially choose the best one is through different statistics. So let's get started. So with the best subset selection procedure, it is a very brute force approach. What I mean by that is that we are going to have to look at all possible submodels. Now, as your number of regressor increases, it might be unattainable to look at all, but you're going to look at a large amount of models and then choose the best model that matches for a specific criterion. And we'll talk about different criterions pretty much this entire lesson. So this is why this brute force all possible models wasn't really useful 20 years ago, because computers can't do what they can now. So this is a great advantage that we have over our previous statisticians in the fact that we can do this. So our goal is we're going to try and look at all possible models and we're going to choose the best one. There is a difficulty though. As you increase the number of predictors, you increase the number of models you're going to look at. So if we only have 5 predictors, there's 31 possible models that we could look at. If we have 10, we have about 1,000, and if we have 15, we have over 32,000. Okay, so that is one difficulty of this approach. However, again, computers are pretty quick these days, and so probably even these numbers aren't that impossible for our computers nowadays. But again, we are collecting more data, so I expect for most research that K to be a little bit larger. So let's look at our first statistic of today, which is the multiple coefficient of determination, or R squared. We've looked at this before. And again, recall that how we interpret it is that R squared gives the percent of variation in our response that is explained by our regression. The drawback of R squared is that it's never going to decrease when variables are added to the model, even if that variable is not useful. So, and I'll explain why in a moment why this is true. But R squared is always going to favor more predictors, and it's always going to tend to overfit models as we increase our predictors, okay? The reason it's going to always increase and never decrease, it might increase a little bit, but it will never decrease, is because of how it's calculated. So recall that our total sums of squares, our TSS, does not depend on the model. What it is the sum of our over our observations of our yi minus our overall mean squared. So it has nothing to do with the regression line. There's no y hat. And so this doesn't depend on the model. We also know that our sums of squares regression and our sums of squared errors is going to equal this number. And based on how we calculate our sums of squares regression, as we add more predictors, this sums of squares is going to increase. And since it has to equal the total sums of squares, as this value increases, then our sums of squared error is going to decrease. Okay, so typically what we are looking for are large jumps in R squared to justify whether we should or shouldn't add predictors. So just because R squared is going up, it doesn't mean that that variable that you added is necessarily useful in the model, because it could only go up maybe like 0.1, which isn't a very large jump, okay? So the drawback of R squared is it really doesn't penalize for the fact that you're increasing the number of predictors in your model. This is where R squared kind of comes into play. the adjusted R squared. My apologies. This is where adjusted R squared comes into play because it's now going to penalize the model for adding more predictors. And how it's penalizing is by adding this little bit right here, by looking and adding in the number of parameters, okay? So our adjusted R squared statistic can decrease when we add a predictor variable. Our adjusted R squared can also be negative. So it's not going to have the same interpretation of R squared. So we don't want to use an interpretation of R squared of the variability for the adjusted R squared. Adjusted R squared is solely used for the purpose of comparing models, like we're talking about in this lesson. Okay. When you're looking at models, though, at the various models, you want to find the submodel that's going to maximize the adjusted R squared. Now, while the adjusted R squared also does compensate and penalize for the increase of our models, it is still probably going to tend to overfit some submodels, okay? There is one thing I want to mention about the adjusted R squared and how it relates to the MSE. Hopefully you guys could recognize that this term right here is our MSE of the model. It's the sums of squares error divided by the degrees of freedom of the error. And so hopefully you guys can at least see, hey, there should be some relationship between these two. And maybe in some of y'all's research fields, it might be more common to work and compare with the MSE. I'm saying that is absolutely allowed because a subset model that maximizes our adjusted R squared will also minimize our mean squared error. Okay, so you can use our MSE or the MSE of the model or the root mean squared to compare these. The one thing that I want you guys to remember, though, and sometimes students mix up, is we want to maximize our adjusted R squared, but we want to minimize, or we want the smaller value of the root mean squared or the mean squared error, okay? So MSE, smaller is better. The adjusted R squared, larger is the better. Now, our third statistic that we're going to look at is called the MaloCP statistic. MaloCP is pretty cool, and it's really interesting because it's going to be doing this balancing of underfitting and overfitting to try and figure out what the best model is. In theory, the optimal value of our MaloCP is going to be P, and that's going to be the number of betas, so the number of predictors plus 1 for our intercept in that submodel under consideration. So in practice, when we're trying to figure out the best model given MaloCP, we want to find the value that is small and near whatever P is for that model. We'll talk more about this in our example in a moment. Here's the caveat though. MaloCP for a full model is going to be P, okay? It's just based on how it's calculated. So MaloCP cannot be used to evaluate the usefulness of the full model. The reason this turns out to be P, theoretically, is because this sigma hat squared is the MSE of the full model, okay? Where this SSE depends on the model that you're looking at. So in the full model, we know that MSE is equal to SSE divided by N minus P. Okay, note, this is the hard thing to note. This SSE is not equal to this SSE unless you are in the full model case. Okay, this SSE here is based on whatever submodel you're looking at. And so that's why in a full model, this orange and this green would match, they would cancel out, then you'd be left with N minus P minus N plus 2P, which results in P. Okay, so that's why for the full model, this orange and green value would match, and we can't use this. But it is practical for anything or a subset of the full model because this orange and green value aren't the same. If that doesn't make sense to you, don't worry about it. All I want you to remember at least is when you're comparing models with MaloCP, you're trying to look for the value that is the smallest and near P. Let's go to an example now. So we're back with our cement example, where again, we have our 4 predictor variables of these 4 different chemicals, and we're trying to understand our Y, which is our heat. Here's a nice little table that has our R squared, our adjusted R squared, and our CP. This is not a very nice table that you're going to get from JUMP or R. I kind of made it, given the values that we got from JUMP and R. Typically, what's going to happen when you get your models from R or JUMP is it's going to break it up into kind of sections. So in this section, we have just the single variables. In this section, we have 2 variables. In this section, we have 3 variables. And in this section, we have our full model. So let's just take this step by step. With our adjusted R squared, I want to bring up something. So let's say right here, we see that in our single variate models or regressor models, X4 is the largest R squared, that value right there. And so with only these 4 models, we would say that X4 is the best model chosen by the R squared criterion. Okay. Now, if we go down here and we maybe look at X1, X4, notice that there is a large jump in our R squared. Okay. This would probably tell us that, hey, including X1 is pretty important in the model, and we would recommend it, right? Here's something to also notice. If we look at X1, we see that there's an R squared. Just by itself, there's an R squared of 0.28. If we look at X4, there's an R squared of 0.67. The R squared, given both of these variables, is always going to be larger. Again, that just goes on with what our theory. Now, I want to bring up another one. Let's say we were looking at X1, X3. This R squared, we would compare it not to all of the R squareds, but only the R squareds that involve the X1 and X3. So if we looked at X1 and X3, these are lower R squareds. I'm just trying to give an example. This R squared must always be bigger than at least this X3 and this X1. Okay, that's a question on your homework. I'm trying to help prepare you for. So overall idea, our R squared jumped up a lot from 1 variable to 2 variables. And then our R squared from 2 variables to 3 variables really didn't jump up too much for our top models. What we want to look at now, what I want to talk about is CP and understanding this a little bit better. So in our 1 variable models, that is these models right here, P is going to be equal to 2. It's 2 because we have 1 variable plus the intercept. Okay. So when we're looking at these CP values, we want to find the model that is closest to 2. And in this case, none of them are really close to 2. So we would say that a single variable model probably isn't the best. So then we would move our way to looking at the 2 variables. In this case, our P is equal to 3 because we would have 1 variable, 2 variable, and then we would also have our intercept. Okay. And when we're looking at these values, we want the CP that is closest to 3. And hopefully you guys can easily see that that would be this model right here, X1, X2. Now, if you remember from our step selection procedures, or just flip back to those notes, you'll probably recognize that X1 and X2, the model with those 2 variables, was actually one that was also chosen. Now, if we look, just to give another example, if we were to move down here to the 3 variables, P is equal to 4. And so we would want to find the value that has that is closest to 4. What we kind of see here though is these 3 models are pretty kind of close to each other, and they're also close to p equaling to 4. So this is where things get a little bit more complicated, and it also depends on your data and what your problem is, because now we have to make a decision. We have all these criterions, we're looking at them, we're trying to understand our data, and we need to make a decision on what model we want. Okay. We talked about how there was an increase in our R squareds from models with 1 variable to 2 variable, and we see that our CP values for our 1 models aren't that good. So we at least have intuition of, hey, probably not these models, right? Now, when we're looking at these the models with 2 variables or 3 variables, we can see that that the model with 1 and 2 in it is our best here. But when we also look at our adjusted R squareds and our R squares, moving from 2 variables to 3, they're not increasing much. And also, there really isn't a much difference in the MaloCP and it getting closer to p equals 4. So what I would do probably at this point was I would go up to my chemist or my specialist and the company that I'm working with, and I'd have a conversation with them. And it'd be something like, look, I have this model right here, X1, X2, that I would recommend. Then I also have kind of X1, X2, X4, which I would recommend over these two based on it having a higher R squared and adjusted R squared. And honestly, these CP values are pretty close. And our stepwise procedure gave us some intuition of this model right here. So that's what I'm thinking. So really, I'm trying to decide between this model and this model. And I would tell them, I have these 2 models where one has an extra X4. And unless you can provide some expert knowledge or evidence that X4 is really, really going to impact our response, I would advise using the smaller model, because that's typically advised, and go on about my day. Hopefully that makes sense. So there is some type of weighing in, thinking about the process, but whatever process and whatever model you choose, you always have to explain why you chose it. Okay, so that is something that is very important when developing and picking models. The last thing I want to mention about this is our CP value for a full is 5. We cannot use MaloCP to properly evaluate the full model. Okay. This is the output you're going to get in JUMP, where you have your R squared, you have your root MSE. You also have these 2 columns, AIC and BIC. And in our homework, I ask you to use at least one of them, I think, if I remember properly, to choose the model you want. With AIC and BIC, you want to pick the model with the lowest value. Okay, so in this case, our BIC right here is our lowest value, or roughly our lowest value, not including the full model. Okay, they're actually not too different in my, these 2 values really aren't, oh wait, no, misread that. I thought that was a 6. This is our lowest value, so don't listen to what I just said. And also in our AIC, that's the lowest value, so that would be probably picked. So based on all these different criteria, looking at them, I probably again would pick X1, X2. We have the smallest and closest to our P for MaloCP. AIC, BIC are also the smallest. We have a decent adjusted R squared, and by adding more parameters, we don't increase by much. So my model for the cement data would be X1, X2. You just need to be explicit in why you chose your models. Something else, this is foreshadowing to lesson 17 that we would probably want to investigate is multicollinearity before providing our final results. But since we didn't talk about that yet, I'm going to say X1, X2 is my final model for this problem.